Good evening, everyone. Today we will be having our last live session for this course, Circular Dichroism and Mass Spectroscopy for Chemists. And this is an extra class where I will be teaching you the basic concepts about the how to form a character table, because that was not a part of syllabus, but since it's very important related to the symmetry and to find out the point groups, so we will be covering that. And also I'll be giving you a complete overview of whatever the things that we have covered in this course, be it CD spectroscopy and mass spectroscopy and symmetry related things. So we will wait for 5 more minutes for others to join, and then we can start with the session. Thank you. So in last yesterday's live session, we had taken some assignment questions. So this was being given as a homework. Have you tried it? Hello? two questions have been given as a part of homework. So we will firstly discuss these questions and then we will move on to our session for today. Okay. So it was said that in mass bar spectrum of a sample containing iron recorded in the presence of a static magnetic field, the number of possible allowed transitions is. So we already know that in presence of magnetic field, there would be splitting of the I levels. Say when we are saying that we are taking iron 57, so it is having ground state as I equal to half and I equals to 3/2 excited state, because it is still mass bar spectrum, that means gamma radiations are there. So when we say in case of source, I equals to 3/2 is the excited state, it emits. So it emits gamma rays, and then there's an excitation to this level. Now when it is happening, so in presence of static magnetic field, these levels would also be splitting. Say I equals to half when we have 2 and I plus 1. So when it is so this I equals to half will be splitting into plus 1/2 minus 1/2 and I equals to 3/2. That mi values would be plus 1 3/2 plus 1/2 minus 1/2 minus 3/2, right? So now when we have 3/2 level and this is 1/2 level, in presence of magnetic field, these will split into similarly. So degeneracy goes away, plus 1/2 minus 1/2 plus 3/2 plus 1/2 minus 1/2 and minus 3/2. So in presence of the magnetic field, the splitting will happen. Okay, now it says we need to find out how many peaks would be observed if this is the scenario in mass bar spectrum. When we know already I equals to half and 3/2, the excitation is happening. So earlier it was only one peak. Now when the levels have been splitted into corresponding to their mi values, they have been, one level has been split into 4, the ground state level has split into 2. So correspondingly, now we can see the transition from ground to excited state, how it is happening and how many number of peaks are possible. So if I'll just draw from ground to excited state, the first level is plus 1/2. So I'm making it in blue color. So whatever the transition I'll show in blue color, that is coming from mi equals to plus 1/2. So if first this one, second is this one, then third and fourth. So just by looking at it, we can expect to have 4 number of transitions from mi equals to 1/2 down state to excited state, right? But actually the transition rules says delta mi should be either 0 or it should be plus or minus 1. It cannot exceed that level. So if you will see, taking up this plus 1 by 2 and minus 3 by 2, it would be like minus 3 by 2 minus of plus 1 by 2 because we are taking a delta. So this value is minus 4 by 2, that is minus 2. So we cannot exceed from 0, plus 1 or minus 1 value. So this value is not possible. Therefore, this transition from plus 1 by 2 to minus 3 by 2, it is not possible. Otherwise, if I'm naming them as 1, 2, 3, and 4, so we found that fourth transition is not possible, right? Now, what about third, second, and first one? Look at first one. It is from plus 1 by 2 to plus 3 by 2. So if I just subtract it, it will come as 2 by 2. That is 1, which is allowed. So first transition is allowed. If I'll take now second one from plus 1 by 2 to plus 1 by 2. So it is clear that delta mi would be 1 by 2 minus 1 by 2, that is 0. So this is also allowed. Because transition rule says that it can be either 0 or plus minus 1. Just give 1 minute. So I hope this is clear up to this point, that how we are coming to the transition things. So we had seen that 4 possible transitions are there from ground state plus 1 by 2 to all the excited states, and from all the 4, which one are allowed and which one are forbidden. So we found that first is allowed, second is allowed. Now what about third? Third one is from plus 1 by 2 to minus 1 by 2. So this is your excited state. This is your ground state. So now take delta mi minus 1 by 2 minus of plus 1 by 2. So this is excited state. This is ground state value. Minus 1 by 2 and minus 1 by 2 is giving you minus 1. Therefore, transition third is also allowed. So out of 4 expected transitions, 3 are allowed. Similarly, if now I will take this one, I'll again make it. So I was saying that this was plus 1 by 2, minus 1 by 2, plus 3 by 2, plus 1 by 2, minus 1 by 2, and minus 3 by 2. Now I'm taking with green color, and this green color is for my minus 1 by 2. So when I'm going from minus 1 by 2 to this first transition, this is your second transition, third transition, and fourth transition. So this is 1, this is 2, this is third, and this is 4. So now we will take up for the ground state of minus 1 by 2 value. Now first one we have from minus 1 by 2 to plus 3 by 2. So delta mi we will find out plus 3 by 2 minus 4 by 2, which is 2. So first itself is forbidden. It is not allowed according to the transition rules. Now look at the second one. Second one is from minus 1 by 2 to plus 1 by 2. delta mi 1 by 2 minus of this one 1 by 2 becomes 1. So this is allowed. And third one we are seeing minus 1 by 2, 2 minus 1 by 2. And therefore, delta mi is minus 1 by 2 plus minus of minus 1 by 2. This is 0. This is also allowed. And the fourth one we have minus 1 by 2 to minus 3 by 2. Therefore, delta mi is minus 3 by 2. This will come as minus 1, which is also allowed. So out of the 4 transitions, we found that one is giving plus 1 value, one is giving 0, one is giving minus 1 value, which are allowed. But one transition from minus 1 by 2 to 3 by 2, it is giving us delta mi value as 2, which is not allowed. So there also for the transition, therefore, for ground state minus 1 by 2, only 3 transitions are allowed. So, and for ground state plus 1 by 2 also, only 3 transitions are allowed. So in total, 6 transitions are allowed and we will see 6 peaks. Therefore, the number of possible allowed transition in this particular case, the answer is 6. I hope this is clear. So in this particular way, we need to understand and we need to remember what is the transition rule, which is very, very important to find out how many peak it is going to, in how many numbers it is going to split. So earlier we were expecting it to be only one peak, and normally when it is in no magnetic field and just the splitting happens from 1 by 2 to 3 by 2, 2 transitions. So in that, because of the electric field gradient, so it splits into these two. But now since we have the magnetic field also, so it would be having, right now I'm not very sure about the intensity of these things, but this would split into 3. And that average would be giving you the exact delta value which we are expecting. Okay, so this is your transmittance and this axis is your velocity millimeter per second. So the answer would be 6 peaks or 6 transitions. Now we will take up the second question that has been given as homework. So this was also the homework from last lecture. How do you differentiate between the facial and meridional isomers using the IR spectroscopy? So firstly, whenever these things have been given, you need to know the point group of the symmetry of this particular geometry. So we know generally octahedral where there are two types of ligands, L and L dash. So in those particular case, it tends to have two types of isomers. One is called facial isomer, other one is meridional isomer. How it looks like generally when all the ligands are same, that means all are L, so it will form here actually L equatorial, 4 equatorial ligand L, and the symmetry is, or I would say the point group is octahedral. So it is highly symmetric. Okay. So when we are changing from high symmetry to, we are coming down to, we are lowering the symmetry. So from this one, now 3 of them have been replaced. So I have a possibility that I am placing all the 3 ligands in a triangular fashion and other L dash ligands as this way. So if you'll see, these are making kind of a triangle, right? And this particular isomer is facial isomer. Correspondingly, what we have is chromium CO whole 3, NH3, 2 positive. So here, when we are having chromium, it will be having carbon monoxide here, this way, here with the NH3, this side NH3, or we would make it like, okay. So this particular isomer is now facial. Now we said that octahedral symmetry has been reduced and it has come down to a lower symmetry. So here, if you will see, C3 axis is there when it is passing through chromium, and all the COs corresponding to making a triangle, they will rotate by 120 degrees. So therefore, this particular isomer is tend to form a C3b point group. Corresponding to your C3Z, there would be 3 sigma Z also. So we will get E, C3Z, 3 sigmas. So this corresponds to your C3B point group. Now, if you will clearly see here, how many different types of your COs are present. So one CO is your axial CO, and the other 2 COs are your equatorial COs. So therefore, it will give you 2 CO IR bands, one for axial and one for equatorial. So in this way, we got the 2 peaks. Now, if I make the meridional, considering L and L dash, I will be having L here, second L here, and now I have put L dash. Here also we have L, then we have L dash, and then we again have L dash. So this kind of symmetry is there when it is passing through one C2 axis, which is containing one L and L dash, and therefore it is giving us L and L swapping and L dash and L dash swapping. So it would be having C2 from this particular direction, and therefore, corresponding to that, we will be having 2 sigmas also, and E is anyway there. Therefore, it is giving you point group of C2V. This is the point group of your meridional. Right? So when we have this kind of system, now replace the M by chromium, L by carbon monoxide, L dash by NH3, right? So we will be having here carbon monoxide, here we now have NH3, and here we have carbonyl, here we again have NH3, and again NH3. So if you will see here carefully, now it is giving us different types of, all the three COs are different now, because this CO is corresponding and having an environment of carbon monoxide and NH3. This CO is with NH3, and this carbonyl is in presence of one CO and NH3. So its interaction and the dipole moment would be varying because of the different surroundings. So here we expect to have 3 IR bands, and in this particular way, we can identify how many number of bands are appearing for facial and meridional, and then we can assign. So this is the way we can use the symmetry and the spectroscopy together to find out the best possible way to identify the different isomers with the same molecular formula. I hope this is clear. Now we can start with the character table question. So earlier, so generally what we started with was the symmetry, and in symmetry we had symmetry elements. The main symmetry elements were identity, inverse, inversion center, your principal axis of rotation, or we can say proper axis of rotation. We have improper axis of rotation, and we have sigma, which is the plane of reflection. So this is your identity. This is your inversion center or inverse. This is your proper axis of rotation. This one is improper axis. And this is your plane of reflection. Right? So when we have these symmetry elements, corresponding to that, we say that how do we find out the point group where all these elements would be present? So point group, it's a mathematical form where we can inculcate all the possible symmetry elements of your any molecule. So it's a total of all symmetry elements present in a particular molecule. So we have also seen how to find out how to come up to a particular point group. So firstly, when we are starting with okay, so when we are starting with, we need to first see before jumping to the character table, it is very important to revise those concepts to where we can actually get to know about whether this is right or not. So first question would be, is the molecule linear? If your molecule is linear, that means if it is yes, then you need to find out whether it is having inversion center or not. I is inversion center. So if the answer is yes, then it is having so if the answer is yes, then it is having D infinity H point group. If it is no, then it is having C infinity V point group. So these two are called as linear point groups or the linear molecules, where if it is linear, then we need to first check. Say, for example, the general case would be A, B, and B. So this seems to be linear and it is having inversion center, because if we go to opposite ends to the same distance, it will give you the exactly same atom. Or if you have B, B, A, or any other combination, so it is not having inversion center. So this comes into category of C infinity V, and the other one comes into category of D infinity H. Now the next question is, if it is not linear, then whether it is a cubic or special symmetric group. That means octahedral, tetrahedral, or icosahedron, something like that. So if it is there, then they comes into this cubic groups. And if it is no, so we got to know that neither it is linear nor it is this special group. Then find out whether any proper axis of rotation is existing. So n greater than 2. If it is no, then see whether sigma is there, that plane of reflection is there. If it is yes, then answer would be CS, because a proper axis is not there. Other than identity, nothing is there except the sigma plane, that is CS. If it is no, then find out whether I is there. If I is there, then it is CI. And if it is not, then it is just C1. So these CS, CI, C1, they are called as non-rotational groups, because they are not having any proper axis of rotation element. So non-rotational will be having CS, CI, C1s. That means they are devoid of any proper axis of rotation. Also, they are neither linear nor cubic, nothing. So just they are having one extra element besides the identity, which is present in anything, everything. So this is one group. Now, firstly, we have taken the case where CN is absent. We will now take the case where CN is present. So if it is present, where we are saying n is greater than 2. Okay, because if we have n equals to greater than equals to 2, then yes is there. Then find out whether n C2s are there perpendicular to your Cn. Say if I am considering the case of D2H, so one C2 would be there, other two C2s should also be present. If it is no, then find out whether sigma H is there or not. If yes, then it is CNH. CNH. If it is no, then it is, if it is no, then check sigma V is present or not. If sigma V is there, then it is CNV. And if it is also not there, then it is simply CN. So CNH, CNV, CN, they are called as single axis rotation group, because they're only having one CN. They do not have any C2s. Now, considering that CN was yes, it was present, and second possibility, NC2 perpendicular to CN, that is also yes. Now, if it is yes, firstly find out whether sigma H is there or not. If it is yes, then it is called as DNH. If it is no, then find out whether N sigma Ds are there. Then if yes, D and D is there. If no, then just Dn. So we will be having DNH, DND, Dn as your dihedral groups. So this is the way we have to find out the point group. Why am I focusing and revising the point group? Because we are going to start about the character table, and character table is very, very important. It is dependent on your point group only. So to identify the point group, it's very important. These steps we have to go one by one. Say, for example, I'll just take a simple example of water molecule. And if I'm drawing water molecule here, so I'm defining the axis as, this is my z-axis, x-axis and y-axis. So I'm saying that firstly, I need to find out the point group, and for finding out the point group, I need to ask myself whether this molecule is linear. So answer is no, because it is not linear, it is a bent shape. Second, whether it is a cubic. Do you feel that it belongs to octahedral, tetrahedral? No. So that is also not there. So if these two are not there, now see whether any Cn is present or not. Cn means C2 is present or not. So we saw that C2Z, that means C2 correspond to 360 degrees divided by 2, that is 180-degree rotation. On giving the C2Z along the oxygen, the HA and HB, they swap with each other and they will give you an equivalent orientation. Therefore, C2Z is present. So is there any NC2? No. There was only one C2 present, so we don't have any NC2. Now check whether any sigma H is there. Sigma H is also not there because perpendicular, your C2 is this along, and if I'm saying perpendicular to this one, there is no plane, that is just the vertical plane only. So it is also not there. And sigma V, yes, there are two sigma V's present. So therefore, we ended up having identity C2Z, two sigmas, and it gives us point group of C2V. So this way we have to go from linear to coming to NC2, finding out the sigma H and everything, so that we will be getting a point group. Now coming to the main topic. Okay, this meeting will be ended up in 6 minutes. So before we start with this character table, since you were not present, so I have already explained the answers to the two questions. So have you tried the questions by yourself? The first question where you need to find out how many possible allowed transitions are there for having an iron sample in static magnetic field. So I've already given answer 6. Were you able to find it, or should I explain it one more time?
Explain, ma'am.
Okay. So we were saying that we already know that the transition in case of iron, it goes from 1/2 to 3/2. So this we have already known. In case of the 57 iron, these are the ground state and this is your excited state. And when you have source is already in excited state, it will emit the gamma rays and then sample, the same sample, as we know that sample and source have to be same. The sample would also be your 57 iron. Now it will excite from ground state to the excited state, I equals to 3/2. So the earlier we used to see only one kind of peak in MOSFET spectrum, like this way, only one peak. But if it is involving electric field gradient, so we at that point we got to know that in electric field gradient, it would be having two splittings. Say this, because in electric field gradient it has to be non-spherical. So the I value has to be greater than 1/2. Only these level can be split up. So at that time, only I equals to 3/2 got split into plus 3/2 and plus minus 1/2. And the ground level I equals to 1/2 remained as such. So we only had two transition possible. So whenever there is electric field gradient, our peak goes, earlier it was this one. If there is no EFG, is 0. If EFG is present, this will split into 2. So up to this point, it is clear to you that how the two splitting peaks comes when we have electric field gradient.
Okay, ma'am, I understood.
Okay. So this was the case when there is no magnetic field and only electric, no magnetic field was there. And just the electric field gradient, which is appearing from the molecule itself. So that was the condition. But in the question, it has been said that in presence of static magnetic field, how many number of possible allowed transitions you can expect of. So earlier we have in presence of electric field 2. So what would be the number when we are giving magnetic field? So whenever magnetic field comes into picture, the MI values, they split. They actually split into everything because it does not require it has to be greater than 0 only. I 1 by 2 would also be splitting. So in presence of magnetic field, this I equals to half value will split into 1 by 2 and minus 1 by 2. And 3 by 2 will split into its 4 level, going from plus 3 by 2, plus 1 by 2, minus 1 by 2, and minus 3 by 2. So when we have split it into in the presence of magnetic field, all the levels are there. Now we need to see which transitions are possible. So firstly, we have taken, because the transition has to happen from ground state to excited state. So my first ground state is plus 1 by 2. Now what transition could be possible? So this plus 1 by 2 can go to this excited state plus 3 by 2, plus 1 by 2, minus 1 by 2, and minus 3 by 2. All the 4 possibilities are there, but we need to find which one are allowed and which one are forbidden. So there is something called transition rules. So transition rule says that the difference of these values should either be 0 or it should be plus 1 or it should be minus 1. It should not exceed these values. So what we did, we then check for all the 4 possible transitions that we are expecting to have. We check whether the difference is coming in this particular range or it is going beyond. So the first transition, if you'll see, it is going from plus 1 by 2 to plus 3 by 2. So I have written over here plus 1 by 2 to plus 3 by 2. Now for delta Mi, you have to subtract the excited I value to excited Mi value to the ground state value. So the excited value is 3 by 2 minus plus 1 by 2. 3 minus 1 is 2, 2 by 2 is 1. So 1 comes under this rule that it can, if this value, the delta Mi value, if it is 0 or plus 1 or minus 1, then it is allowed. So we got to know that this transition from plus 1 by 2 to 3 by 2, it is allowed. So this transition is possible. Now we went to second. Second transition, we are expecting from plus 1 by 2 to the next level, plus 1 by 2. So plus 1 by 2 to plus 1 by 2, when we subtracted, the delta Mi value came out to be 0. This is also allowed because it is coming under the rule. So it is fine. So this one also is allowed. Now think about the third one. You are going from the third one, where are we then? So the third one that we were having, it is from, so the third ground state, third possible transition that we were having, it's from plus 1 by 2 to minus 1 by 2 of the excited state. Now I've written here the excited state value minus 1 by 2 and subtracting it from the ground state value plus 1 by 2. Minus 1 by 2 and minus 1 by 2 will give you minus 1 value. So this also comes under your allowed transition. So 3 are possible. Now what about the fourth one? Fourth one is from plus 1 by 2 to minus 3 by 2. And when you have minus 3 by 2, and plus 1 by 2, on subtracting the 2, you will get minus 2, which is not allowed because the transition values only comes under 0, plus 1 and minus 1. So when it is minus 2 value, that means fourth one is not allowed. Only out of 4 possible transitions, we can see 3 transitions from the ground state plus 1 by 2. Is this clear?
Clear.
So can you please find out how many transitions are possible when I have taken the ground state as minus 1 by 2?
3 transition possible.
So which one would be not allowed in the case of minus 1 by 2?
2 minus 3 by 2 plus 1 by 2 2 to minus 3 by 2.